So we're going to take a little aside here to talk about, we talked about how vectors transform under rotation matrices. So let's take a look at how tensors transform under rotations. So we have an initial orthogonal set of vectors. We'll call it U and V. Also, watch this. You like that? So, another set of vectors that we'll call U prime and V prime, and there's some angle between them, and we defined a rotation matrices for vectors, right, and like how they would transform. So we already looked at that. So we have a rotation matrix, and we're just going to call it R. It's that unitary rotation matrix. Then U prime would be RU, and V prime would be RV. And so then the question is, if we have a matrix equation, or tensor equation. Remember, sometimes I use the word matrix and tensor interchangeably when I'm talking about a second order tensor, right? Because we can do matrix vector operations and other things on second order tensors. But understand that doesn't hold as you go to higher, like third order, fourth order tensors. You cannot use, they're not matrices. You cannot use like typical matrix vector operations on them. So only when I'm using those words interchangeable, matrix, I'm talking about a second order tensor only, right? So if you have a vector, we have a matrix or second order tensor T times U. I mean, that's a valid equation. So then the question is, like, how would one go from, say, V prime to some new tensor T prime U prime? So in other words, if I change the basis, right? Are y'all familiar with that kind of terminology? Like you have basis vectors, like the underlying coordinate system, right? So if I change the underlying coordinate system, how does the tensor T or matrix T change? Okay. So what we'll do is we can just start by plugging in our vector rotation matrix relationships up there. U prime equals RU, V prime equals RV into this equation down here. So V prime is equal to RV T prime times U prime, which is equal to RU. Okay. So then I can multiply on the left by R inverse. All right, so remember a matrix inverse times itself is the identity matrix, right? And the identity matrix times a vector is just the vector. So that's when we have V equals R inverse T prime R U. And then remember also that if the matrix R is unitary, remember, a unitary matrix is a matrix that its inverse is its transpose, or its transpose is its inverse. And that's always true of rotation matrices. So rotation matrices are always unitary. So we can also write RT, T prime, RU. Okay. So by inspection then, if we just compare, this equation with this equation, I guess just to be precise, these are vectors. Go back and add all my vectors. Okay, so if we just by inspection compare the two equations that I've underlined, then evidently T must equal R transpose T prime R. And then if we wanted to solve for T prime, then we just multiply on the left hand side of both equations by R, and multiply on the right hand side of both equations by R transpose. And ultimately we could invert this equation to get T prime is equal to R T R transpose. Right? So this is how a tensor changes under a rotation. Okay? And that's then relevant to what we want to talk about today. So last time we derived the Cauchy stress equation. We know what the stress looks like. And so now what we're going to talk about is like a special rotation of the stress matrix to get it into a special form. I'll write it down and we'll talk about it, right? So here we're going to just change the symbols to say sigma prime is equal to R sigma R transpose. And if you choose R perfectly, then we can get a matrix that looks like that, where sigma 1 is greater than sigma 2 is greater than sigma 3. So does anybody know what sigma 1, sigma 2, and sigma 3 are called? Principal stresses, right? And we talk about them in reservoir geomechanics all the time, right? SH min, SH max, S vertical, right? So we can take any stress tensor, and if we rotate it perfectly, we can diagonalize it, and what'll be on the diagonal will be the principal stresses. Does anybody know how we choose that R perfectly? Yeah, you solve an eigenvalue problem. Sometimes it's called like a spectral decomposition, right? So just to review that, we solve the problem. We take the determinant of sigma minus lambda I equal to the zero vector, or tensor. And we solve that. Basically, you solve that, that's not the zero tensor, it's zero, it's a scalar, right? Because when I take the determinant of this, I have a scalar equation, right? And it'll be a polynomial in lambda. Does anybody know what that polynomial is called? Characteristic polynomial, right? So it'll be a polynomial in lambda. I'll write it down in a second. And then basically it will have as many lambdas as there are, as the rank of the matrix. So if it's, in this case, and this is in general, in this case we're talking about a stress tensor, so we're talking about a 3 by 3. And so there'll be 3 eigenvalues, right? So ultimately you'll solve for this. You'll have lambda 1, lambda 2, lambda 3, and then you take those guys and you plug them back into this equation. So you take sigma minus lambda 1 times I multiplied by V1 equal to, now this is the zero vector, right? Also, sometimes this is said to be the null space, right? You're trying to find the vector V, which results in the vector V that's in the null space of this equation, right? That's the math lingo. But so basically you would do this for lambda 1. You do it for lambda 2, find another v. Remember, these are vectors, so that each of them have 3 components. And do it again. And then, if you order the lambdas in order from greatest to smallest, in this case, in my example here, we'll just assume that lambda 1 is the largest value, lambda 2 is the second largest value, and lambda 3 is the third largest value. Then, basically, assemble your rotation matrix such that it looks like this. So where, remember, these are vectors, and by default, as I mentioned several times, they're column vectors, right? So this, if this has v1 is like the vector which corresponds to lambda 1, right? But it has 3 components itself, right? So this thing is a matrix, right? As I've written it. So if you build your rotation matrix from the eigenvectors, by solving the eigenvalue problem, and then you perform the rotation on the stress matrix, plug it into that formula where R sigma RT, then sigma prime will equal the eigenvalues on the diagonal like that. That's the way it'll come out. And while we're talking about this in the context of stress, it works for any matrix decomposition, right? So a lot of times you'll see it written more generically as just like, you have a matrix A can be decomposed into like Q lambda Q transpose, where Q is again your eigenvector matrix, and lambda is then a diagonal matrix of the eigenvalues. So whenever I write like that, where I just write something on the diagonal and big zeros in the other off diagonal, that just means everything off the diagonal is 0, right? So in this case, it's a 3x3, where everything but the diagonal is 0. So yeah, so you can go either way, right? If you have this spectral decomposition, if you know the eigenvalues and eigenvectors, you can reassemble the matrix A. Or if you know the matrix A and the eigenvectors, you can find the eigenvalues like that.
R has to be a unitary matrix, right? In this case?
Well, okay, so a unitary matrix is essentially also can be thought of as like a matrix where the columns of the matrix are unit vectors, okay? So in order to, that is one maybe caveat, in order to ensure that they're unit vectors so that you can ensure that R is unitary, then you can just divide by the magnitude of these vectors, right? So, eigenvectors are really just directions, right? And so it really, and almost always we solve for these in a computer program. And so I got a little lazy there. Like if you solve that spectral decomposition in MATLAB or NumPy or something like that, it's going to give you, it's automatically going to give you the unit vectors back. So it will be like if you solve an eigenvalue problem in NumPy or Python, it's going to give you a unitary matrix. Right? If you work it out by hand, then to ensure that it's unitary, you would just have to divide each vector by its magnitude to make sure they're unit vectors. And really, also just keep in mind then, even if you didn't do this, if you didn't divide by the unit vectors, all it would mean is that instead of transposing the matrix, you have to compute it, the inverse, right? Which you can do also with a computer. So that's the advantage of a unitary matrix, is that it transposes its inverse. Right? You don't have to do an extra computation. It's easy to transpose a matrix. Right? Okay.